and welcome to a new open class. Sorry for the delay. It's been a long time since my last open class, so we had to prepare some things and get used again to everything. But yeah, so we are finally here. Hope everything is fine. The video is fine. You can also hear me correctly, hopefully. So yeah, I will be opening right now the chat so that I can see your comments and messages. But yeah, so today we are going to be having a class about sensor fusion with ROS2. So how to properly improve our robot's pose estimation in ROS2 by using sensor fusion. Yeah. More specifically, the robot localization package. We will see a practical example as always. And we'll be doing some tests with simulations. So yeah, without further ado, let's get started. Then yeah, so let me right now come here to my computer screen, and I'm going to start as well sharing my screen. So give me 1 second here. Yeah, there we go. So PC, okay. Now you should be seeing my computer screen. So yeah, let me go to the open classes so that I can get your messages here. There you go. Okay, fine. I can see Rafal, Wolski saying fine, yes, Kartan, Joshua. Audio is very quiet. How to join it? Hello, hello. Okay, so I'm very well, Vikas. Thank you for asking. So I hope the audio is fine. Just to let you know that you should be able also to increase the volume here directly from your side. Okay, so you should be able to put it higher in case it's low for you, so that you can hear me better. Okay. Jayanta says, ROSJECT not available yet. Okay, so ROSJECT should be available. At least I have it available here, yeah? So in case there is some new people here, let me remind you that for our open classes, we always use ROSJECTs, okay? So you have to base them off, we always provide a ROSJECT so that all of you, all the audience can practice and do in real time everything that I am going to be showing, explaining, and doing, okay? So these classes are not meant for you to be there just listening and watching to what I am saying and doing, but they are meant for you to practice alongside with me, okay? So that's the purpose of these projects and why we share them with you. So in order to get them, all you have to do is to click here in the fork and open the class project, yeah? It's right above the chat here in light blue. So by clicking here, I'm going to click myself here to get my own copy. There we go. Launch. Okay. So as soon as you click on that button, you are going to be redirected to this page. Okay. This is the main ROSJECT page. And you are going to find here a streaming tab with the live stream, the chat also, so that you can comment and everything. I'm going to try to move this to another page so that I have more space here for my project. So yeah. And then yeah, so this might take a few moments to fully load the whole environment. So just be patient there, okay? And yeah, but please, all of you who are here, please make sure to click on the button in order to get a copy for your own account of the ROSJECT, okay? And so that you are going to be able to launch the simulation and do all the tests that we are going to be doing today during this class, okay? So please go ahead. I'm going to leave some time and make sure that everybody is able to properly get a copy and open the ROSJECT. I can see that Oh, I can see Gilbert there saying it has been a long time. Yeah, indeed, it has been a really long time, but we are back finally. So so yeah, I'm going to be back doing classes, monthly classes this time about different topics. Okay, so yeah, this one was a bit rushed for me. So yeah, let's see how it goes. But yeah, I'm going to be doing these classes once every month about very interesting topics. Okay, and yeah, so I hope that with each class I'm going to be getting back into the rhythm. So I might be a little bit rusty today. ROSJECT setup done, I can see. Got it, says Jayanta. Okay, now Florencio, I think, was able to solve the issue. Okay, I have my comments here. So, Annelise, please excuse me if my pronunciation of the names is wrong, but yeah, Annelise says, where should we click in order to have access to the simulation? Okay, so first of all of you need to click in this button here right above the chat, yeah, which says Ford can open the class ROSJECT. This is the very first step. Will the class be available after it ends? Yes, we are going to upload the recording to our YouTube channel as always. Okay, so you are going to have all the classes there. And obviously inside the app also, here inside the Construct app, you are going to find all the classes here. If you come here, you are going to see all the previous classes that we've done, yeah, in the past classes tab. Okay, in the coming class, you are going to have the next class, or the current one in this case, which is this one. ROSJECT not available for me. Okay, please refresh your browsers. Okay, if you don't have the ROSJECT available, you don't have this button here available, you see it gray, not clickable, etc. Please refresh your browser, okay? Okay, then let's get started. So in my case, the ROSJECT has already loaded, okay? So after the ROSJECT loads, you should get something like this, okay? This is the environment, the ROSJECT environment, which basically is a cloud-based environment that is ready, 100% ready to allow you to work with ROS without having to do any setup, okay? Let me drink a little bit. All right. So, yeah, then here you are going to find the notebook here in the right. You can reorganize everything as you'd like, okay? Make things bigger, lower, whatever setup you prefer, you can configure it as you like, okay? This is the code editor that we are going to use in order to check out files, edit files, create new files, etc. Yeah. So this basically gives you access to all the workspace packages, files, etc. from a graphical interface. Yeah. Then down here you have the terminals. Okay. Also very important. You have the terminals, which basically are regular Linux terminals, where you can execute the commands and use it to execute commands, move through the file system, etc. Okay. Now, yeah, and then in a moment we are going to be launching the simulation. Okay. Right now the simulation is not started, so you are not going to see it. We are going to be launching it in a moment. Okay. So, so yeah, I want to wait a little bit to make sure that everyone is ready and has their ROSJECT opened, and we are ready to keep going. You're welcome, Zeliaskov. You're welcome. Okay. So yeah, the class is going to be of around 1 hour. Okay. So please let me know if everyone is. Let me see if I can check the chat here. There you go. Okay. So please let me know. Confirm if everyone is ready and has. If all of you have your projects ready, opened, and we are ready to continue. Give me a thumbs up or okay, ready. Okay, excellent. So we are ready to get started. All right. So yeah, then the topic for today's class is going to be sensor fusion with ROS2. Okay, so we are going to obviously be working with ROS2, and we are going to be applying sensor fusion for improving our robots' post-estimation data. Okay. Then what is a robot's post-estimation? So, well, post-estimation is essentially information of where the robot is, okay, in an environment. This is, as you may already imagine, this is essential information for a robot, yeah? It's essential that the robot is able to know accurately where it is in an environment. Right? This is really important, especially for mobile robots that need to navigate around an environment, etc. Yeah. So yeah. Then, if you have some, I don't know what is your level of ROS or robotics in general, but if you are a little bit familiar with robotics, all of this may ring a bell, and you say, okay, so this information is provided by Odometry, right? So my robot's odometry is the one that gives me information of where my robot is, usually, right? Especially with mobile robots, if you have worked with them, then this might ring a bell, okay? Now, while odometry does indeed provide information about where the robot is, yeah, it doesn't provide the full picture, okay? Actually, odometry provides information of how the robot moves over time, okay? The problem with odometry is that it gives relative motion, okay? So, essentially, odometry, what it's telling you is how the robot thinks it has moved, okay? But that doesn't have to be how the robot actually has moved, right? Because there are things, there are wheels drift, there are frictions, the environment might change, okay? So, how the robot thinks it has moved doesn't have to necessarily be the reality of how much the robot has moved. Right? Yeah? Does this make sense so far? By the way, some of you, for example, Gilbert, which I know you from previous classes. So for some of you, maybe all this environment is new, but this is the new version of the construct. I hope you all like it. I enjoy it around here. So Cartan says yes. Okay, so I assume this means that it makes sense what we are saying. Okay. All right. So yeah, then. What is post-estimation? So post-estimation aims to compute the robot's true position and orientation in the world by combining information from multiple sources, okay? So we were saying that a robot's pose, yeah, describes its position in the X, Y, Z angle and orientation expressed in roll, pitch, yaw, for example, okay? It can be a quaternion also, yeah, but basically it's the position and orientation information of a robot, okay? Then odometry is a source of this kind of information, okay? But it is prone to errors, okay? So what we aim to do with pose estimation, and more specifically in sensor fusion, is to overcome the limitations of single sources of data, like, for example, odometry, yeah? So odometry provides information about where the robot is or how much it has moved, yes, okay? But can we 100% rely on odometry for this kind of information? The answer is no, okay? Yeah, because odometry can fail, okay? Can have errors, yeah? And if we only use odometry in order to get information about where our robot is, then it's very likely that we are going to end up having many problems, okay? So in order to overcome this, what we do is to use data from different sensors, yeah? Like, for example, wheel odometry, which is one of the most common ones, yeah? Which usually it's going to be using encoders in the wheels, yeah? So we use encoders in order to get this wheel odometry data, but we can combine this data with, for example, IMU. Yeah, this is a very one of the most typical setups, yeah? So we are going to combine information of the wheel odometry computed using encoders with IMU, okay? Then we can fuse these two sensors information in order to produce a much more reliable output, yeah? And get a much more accurate and reliable pose estimation for our robot, okay? But so we can fuse many different types of sensors. For example, we can also add into the equation GPS information, or for example, visual or laser measurements, yeah? So we can get information of how our robot is moving from cameras, from LiDAR, from laser measurements, yeah? Or even ground truth references. This is more for simulation environments, but we are going to be exploring this also during today's class, okay? Then, so pose estimation fuses all of this information to overcome the weaknesses of individual sensors, all right? And then here also there is another concept which is very relevant, which is Kalman filters, okay? So what do we have here? Okay, so basically Kalman filters, yeah, help us in order to improve the measurements, which by default are always noisy, okay? Then what Kalman filters do is to help us combine the different sensors, imperfect sensors, sensor information, let's say, in order to get the best estimate of the robot's true pose, real pose, okay? And how they work on a very high level, I'm not going to get super into details about this because we don't have time for it, okay? But basically, a Kalman filter refines the robot pose estimates by cycling through two key steps: prediction step and the correction or update step, okay? Then the prediction step uses the robot's motion model to estimate the next state. And it also predicts the uncertainty of that estimate, yeah? And the correction or update step compares the predicted state with the latest sensor measurement, okay? So I predict that the robot is going to be here in a second, for example, okay? And then I can predict that, yeah, using the robot's motion model, using math equations. I can compute, yeah, where the robot is going to be in a second, for example, yeah? And then I can compare this result I get from the model into the actual information I'm getting from the robot sensors, yeah? I can compare these two, Yeah, and then I can compute a weighted average, giving more weight to sources with lower uncertainty. Okay, this is essentially what Kalman filters do. Okay. Yeah. So you can see this graph here, yeah, with different sources of information like odometry, camera, IMU, GPS. Yeah, we provide all this information to, in this case, robot localization, and we generate a pose estimate for the robot. Okay, which is a combination of different sources of information. Yeah, are you more or less following the explanation? Yeah, no? Does it kind of make sense? Okay. I am seeing some questions here, so let me have a quick look. Okay, this is a good question by Alejandro Beltran. What do you mean by ground truth? References, an observation given by a person? No. So ground truth, basically, what I mean by ground truth is the real robot pose. Okay? So my robot can be moving around a room, okay? Can be moving around we are going to see practical examples actually about this in a moment, and this is going to be much more sense, okay? But in short, ground truth means the real pose of the robot. Not the pose that odometry is telling me my robot is, or that my IMU is telling me the robot is, okay? Not the information that I get from the sensors, but the real pose where my robot is. That is the ground truth, okay? Because my sensors can be wrong, yeah? Then how I get this ground truth information? Well, in simulation, you can get this information, for example, directly from the simulator, okay? Which is pretty convenient. In the real world, this is a bit more complicated, okay? So you can, so for example, a way of getting the approximate ground truth would be by seeing actually where the robot is, yes? So you can get the information of odometry that is telling you that your robot is 1 meter in front of you, but you can clearly see that the robot is not there. Yeah. But in real environments, there are other methods of getting a ground truth, like external perception systems that can see where your robot actually is, right? Or things like this. Okay. But basically, ground truth means the real pose of your robot, okay? Yes, our robot model is nonlinear. Exactly. That is why we are using an EKF, okay? An extended Kalman filter. Okay, so okay, then let's skip all the talking and let's actually get into a bit of practice, okay? Which is when we are going to see things more clearly, okay? Then the very first thing that we are going to do is to launch our simulation, okay? So we are going to be using a ROSBot XL robot from our friends at Husarion, and we are going to be launching a simulation, a gazebo sim simulation. Okay, so this project is based on ROS2 Jazzy and Gazebo Sim. Okay, no Gazebo Classic. Okay, this is relevant also because I'm going to be showing some things that are related to the Gazebo Sim simulator. Okay, so yeah, then let's start the simulation. For this, all we have to do is to execute these commands in a terminal, in a web shell. So you can open a terminal clicking on this button. You have the icon here. It's here in the bottom. You can click here, and this is going to open a terminal. Okay, And in this case, we have 3 different terminals open here. So yeah, then it is just as easy as copying the commands directly from the notebook. Yeah, you can click in this icon here to copy these commands and then paste them here directly, paste to the terminal, okay? Then you press enter, and this is going to start our simulation, okay? Again, remember that you can organize the different windows as you prefer, okay? So that you can visualize everything, okay? Now, after a few seconds of executing these commands, the simulation window should pop up, okay? And then I recommend you to maximize the gazebo sim, okay? You can click, for example, in the maximize icon here, yeah, in order to make it bigger, and then you can also zoom into the robot by using the scroll in your mouse, okay? For example, let me here zoom in. There you go. Yeah, and you can change the view in the simulator, okay, as you prefer. Yeah, but yeah, so essentially here we have the simulation of the ROSBot XL, in this case in an empty world, okay? Yeah, has everyone been able to launch the simulation? Yeah? Let me have a look at your comments. Yeah, any problems launching the simulation? Can I use my local VM? Yeah, I mean you can use your local computer if you want, but you will have to compile all the packages and everything. Okay with the simulation, says Dimitris. Yeah, so everyone has been able to launch the simulation properly. Yeah. Okay, so I will assume yes, says Alejandro. Okay, then let's keep going. All right, so we have our simulation running here in Gazebo Sim. Yeah, so let's get some information about our robot. Yeah, then the best we can do in order to get more information about our robot is to check what topics do we have available, right? So I'm going to run here ROS to topic list. Again, you can copy directly the command or type it, whatever you prefer, okay? So ROS to topic list, and this is going to give me a list of all the topics available in my simulation, yeah, that my robot provides. There you go, yeah. And yeah, so I can see many different topics, TF, scan, different controller topics, joint states, okay? Now, one that I can see clearly here is the ODOM topic. Yeah, here ROSBot XL base controller ODOM. Yeah, so this looks like it might provide odometry information, right? So let's have a look at this specific topic. For example, with ROS to topic echo, not echo, sorry, info of the. Wait, I need to change my keyboard here. Yeah, ROSBot. XL controller, ODOM. Yeah. Okay, and I can see that indeed this topic, yeah, is publishing odometry messages. Okay, so from this topic I can get the odometry data of my robot. Okay, yeah, like for example ROS to topic echo in order to start getting messages from this topic. ODOM. Yeah, and here I'm going to start getting the odometry messages that my robot is publishing, yeah, which contain, for example, information about the position of the robot, yeah. So right now my robot is at the 000 position in X, Y, Z coordinates, and this is the quaternion indicating the current orientation of my robot, okay? Now, here in this simulation, the odometry data is provided by a differential drive controller, yeah, which is being generated by ROS2control. Yeah, so if I run, for example, the command ROS2control list controllers, I'm going to see the controllers that are right now running for this robot, and one of them I can see is this diff drive controller, okay, which is right now active. Okay, this controller, which is provided by ROS2control, is the one that, for example, allows me to send velocities to the wheels of the robot in order to move it, but also it provides odometry information. Okay. Then this essentially simulates like if I am getting, so the odometry data is being computed from wheel encoders. Okay, it actually gets this information from the simulator, yeah, but it is essentially this. So what does this mean? This means that my odometry data is going to be not 100% reliable, correct? Because my wheels can drift, yeah? So I can have different frictions that are affecting how my robot is moving, yeah? So I have to take this into account, yeah, and know that my odometry might not be 100% accurate, okay? So we are going to try to evaluate this. We are going to do some experiments in order to see if we can trust our odometry data or not, okay? So in order to do this, yeah, so someone was asking earlier, what is this ground truth? Yeah. So essentially, my odometry topic, yeah, this topic that we were subscribing right now, this ROSBot Excel-based controller ODOM topic, this ODOM topic is giving me information about how the robot thinks it's moving. Yeah. So does everyone know how wheel encoders work? Yes, no? No, says Julie. Okay. No. Okay. So essentially, wheel encoders capture information of how much the wheels are spinning. Okay? There are different types of encoders, but basically imagine a wheel encoder as a sensor that detects how much the wheel is spinning, right? And then, based on this information, it tells how much it thinks the robot is moving, okay? Based on the wheel movement. Right? So, for example, imagine so imagine a robot, okay? Imagine a robot that is, let me switch my view for a moment. So, to host, I think that now you're seeing me. Yeah. So imagine a robot that is against a wall, okay? Just like this, yeah? And then you try to move it forward, right? You start sending velocity so that the robot moves forward. So the wheels are going to start spinning, yeah? But the robot is against a wall, so it's not going to be actually advancing, right? Because it cannot pass the wall. But the wheels are spinning. So the encoders detect that the wheels are spinning. So they are going to say, hey, the robot is moving forward. Why? Because my wheels are spinning. Yeah? So I'm going to end up with an odometry which is wrong, right? The odometry is going to tell me that my robot is moving forward, but indeed the robot is not going to be moving forward, right? Yeah? Does this clarify a little bit the concept? Alejandro Beltran is asking, this is not related to all this, but he's asking, how can I see which node is publishing a topic? Okay, so we were checking information of the topic with ROS2topic info, right? For example, ROS2topic info of this specific topic gives us some information about this topic, right? Then there is something that you can do, which is to add a -v to this topic, which means verbose, okay? If you add this to the ROS2topic info command, this is going to give you extra information. And some of this extra information is, for example, what node is publishing this topic. Yeah? So for example, here I can see that the node, this node, ROSBot Excel base controller, this node is the one which is publishing this topic, okay? Yeah, we can see here publisher count. Yeah, so this topic has one publisher, which is this node. Yeah, and it has 0 subscribers. So there is no node right now that is subscribed to this topic. Okay. We can. Okay, so you're still seeing me. Sorry. Let me change again to, there we go. Okay, thanks, there you go. Yeah, now I am in my screen again. Sorry. Yeah, so I was showing here the example, yeah, so let me just show it real quick again. So ROS2topic info, yeah, we were checking earlier with the ROS2topic info command information about this topic, yeah, right? And this topic gives us the basic information, like for example, what type of messages this topic uses, which are Odometry, how many publishers it has, and how many subscribers it has, okay? Now we have another command, yeah, that we can use, which is the same one, but adding a -v, okay, which means verbose. And then this is going to give us extra information, like for example, what is the name of the node that is publishing into this topic, which in this case, we can see here is ROSBot Excel base controller. Okay? Yeah? So I'm just mentioning this because I saw the question, okay? And but I'm not going to go a lot of detail into all these things like publishers, subscribers. For that, you have my colleagues, my colleague Takabarasha, who I saw is around here in the chat, who is also going to be doing open classes on all these topics, yeah, publishers, subscribers, etc., so that you can catch up in case that you are a beginner and there are some of these things that you still don't understand. So you can attend to or check his past classes to get a better understanding of all these concepts. Yeah, what are publishers, what are subscribers, what are topics, etc. Okay. All right. So yeah, then let's continue. Okay. So okay. Here is my simulation. All right. Then okay. Yeah. So we were saying that our ODOM topic, this topic, gives us information based on wheel encoders. Okay, based on how much the robot thinks it's moving, based on this. Yeah. Then we cannot fully trust that the odometry data is going to be 100% accurate. Okay. Then we also were mentioning earlier about this ground truth. Yeah. The ground truth is the 100% accurate real pose of the robot, okay? And in this specific setup, which is this gazebo sim simulation, we have access to the ground truth. Yeah. Indeed, if you go check again the list of topics that are available, you are going to see one of the topics, which is this one, ground truth pose. Okay. In this topic, which provides, let's check the information about this specific topic. ROS topic info, ground truth pose. This specific topic gives us post stamped. Yeah, so this is publishes post messages. Okay, and this is the ground truth which I am getting directly from the gazebo simulator. Okay, not from the odometry. Okay, but from the simulator. So I'm going to know exactly the pose of the robot in the simulator. Okay, now this ground truth in Gazebo Sim is a bit tricky to get. Okay, in Gazebo Classic, if you have worked with Gazebo Classic, which is the old Gazebo, or even with ROS 1, okay, getting the ground truth from the Gazebo Classic simulator, it was very, very easy and very straightforward. Okay, in Gazebo Sim is a bit trickier. Okay. Then I have added here to a notebook these notes, which basically explain how to achieve this, okay? There are different ways of achieving it, but probably the easiest one is by using a plugin, which is known as the GC Sim Post Publisher plugin, yeah, the Post Publisher plugin. With this plugin, we can have the pose of our robot in the simulation, directly in the simulation. So we know it's 100% true because we are getting the information directly from the simulator, right? So in case that that you are going to be working with Gazebo Sim, you can check out this example of how I have done this. Yeah, so you can use this Post Publisher plugin in in your Gazebo Sim, and then you are going to have to breach the topic because this plugin is going to publish the information in Gazebo Sim. Okay, so you need to breach that information into your ROS2 system. Okay. Maybe we are going to do another class about all these, Gazebo Sim, and what's going on there, okay? Because actually Gazebo Sim, the simulator, has its own topics, okay? So if you want to use some of the Gazebo Sim specific topics, in ROS you need to bridge them to your ROS2 system, okay? But maybe that's for another class. Okay, anyways, let's keep going. Okay, so yeah, what I want to do now is to see how accurate is my odometry data. Okay, so for this, I can a very straightforward experiment is to compare my odometry data with my ground truth data while I am moving the robot. Yeah, then for this, what I have done is to create a Python script for ROS2, which basically uses the odometry data to move the robot following a square-like movement. Okay, here you have the whole script, but essentially it's a pretty basic script that uses the current odometry data. You can see here that I am subscribing to the ROSBot XL base controller, Odom. Yeah, this is the odometry data that my robot is publishing. And I am using this information in order to make the robot follow a square-like movement. Yeah? So you have here very briefly the information of what this script does. Yeah? So if it moves forward 1 meter, which is 1 square here in the grid, in my simulator, it moves forward 1 meter and then performs a 90% turn. Yeah, and repeats these 4 times. Okay, so a very basic script in order to perform a square-like movement. Yeah, the only thing is that I am using the the robot's odometry data in order to follow this square movement, yeah? To evaluate that I have moved 1 meter, to evaluate that I have rotated 90 degrees, etc. For all these, I use my odometry information, which I'm not sure of how accurate it is, okay? Then what we are going to be doing is to execute this script to make the robot follow a square-like movement, and then we are going to compare the odometry data while the robot is performing the motion with the ground truth data that we get directly from the simulator. Okay? Then let's start here RVs, because in order to visualize all this data, we are going to be using RVs. So let me open, for example, here RVs 2. There we go. And then let's set up here the displays in order to visualize all this data, okay? Then first of all, we are going to change the fixed frame in our RVs to ODOM, okay? We are going to use the ODOM frame as the fixed frame of reference for visualizing all the data. And then we are going to add a couple of displays, okay? I have prepared, in case that you don't want to do this, all this configuration file that is already prepared for you, okay? But I will show it later, so just in case some of you get lost. But I think it's good that you also know how to set up properly all this, okay? Then, so then I am going to add 2 displays. One is going to be the ground truth pose, okay? Very important. Here I have it. And the other one is going to be the ODOM, yeah? So I'm going to go by topic, and I'm going to go and look for my ODOM topic, which is right here, ROSBot Excel-based controller, ODOM, okay? Now I have here the 2 of them. This is the odometry, and this is the ground truth. So I'm going to change the color of the arrow for being able to differentiate them. Let me set the ground truth to green, and the ODOM is going to be red. There we go. Yeah, so here I have in green the ground truth, right? And in red, my odometry, okay? So, let's start moving the robot now following squares. So let me come here to my ROS2 workspace. I'm going to just build my workspace to make sure that I have everything up to date, okay, with a Qualcomm build. My source. And then I'm going to execute my square movement script with the following command I have here. It's ROS to run, Kalman filter scores, move in squares, okay? So, yeah, let me set up these actually for better visualizing all this. So let me put RVs here in one side and then the simulation here in another, side by side, so that I can, let me change a little bit the view as well here. I can have a better view of the movement. For example, let me put it more to the top. There we go. Okay, rotate a bit like this. There we go. And let me actually change also the perspective here so that I have them. There we go. Perfect. Okay, so now let me start moving in squares. There we go. Okay, I run my script and I'm going to start seeing the robot move here in the simulation. There we go. We can see it moving forward. So far, so good. I cannot see great differences between the green arrows and the red arrows, right? So now here the rotation is initiating, right? This is the first 90 degrees in theory rotation, okay? And we can see that already the robot has not really rotated 90 degrees, right? We can see here, also very interesting, how the red arrows, which are indicating the robot's odometry, are showing that the robot is actually, he thinks that it has rotated 90 degrees, but it has not. We can see clearly in the simulation that it has not, and we can also see that it has not in the ground truth, which is the green arrows, right? Let me clean the odometry for a second. Here, there you go. Yeah. So we can see already how the ground truth, yeah, which is the real pose of the robot, is deviating quite a bit from the odometry, which is where the robot thinks he is. Yes? So here we can already see that our odometry is not reliable, okay? It's going to have errors, yeah? Again, we can see how here the odometry thinks that the robot has rotated 90 degrees and it's moving there, perpendicular, but actually in the green arrow we can see how the robot is really not there, and it has not performed a perfect square. Yeah. Okay. Yeah. So here, with this very simple experiment, we can clearly see that what our odometry thinks, which basically odometry, as we already said at the beginning, is how much the robot thinks it has moved. Yeah. So this is not equal. Yeah. There is a significant error with respect to the ground truth, which is the real pose of the robot. Okay. Yeah. Do you see this? Does this make sense? Can you see here how odometry and the ground truth differentiate between them? Let me go back to the comments here. Marwan is saying, what is the physical reason of this difference? So the physical reason of this difference is the friction, for example? Yes, for example, Marwan. So one of the reasons is the friction. Yes, exactly. Because the wheels have friction with the floor. Yeah, so the movement is not perfect. This is known as drift. Okay? And it's a very common effect in mobile robots, okay? And it is one of the main reasons why you cannot rely solely on odometry data, okay? Drifting, exactly. Where does ground truth get its data from? From the simulator, exactly. The ground truth data, as I explained it, is getting the data directly from the simulator. So I know 100% it's correct. Yeah, that is the ground truth. And for that, I am using the Post Publisher plugin. Okay, I added some notes here about how to do this with Gazebo Sim because it's a bit tricky. Okay, but you can use this Post Publisher plugin in order to get the ground truth data of a specific model. Okay. Yeah, good questions. Good questions. Yeah. In case you want to use something which is already prepared for you, you can come here in RVs and go to File, Open Config, Yeah, and then here you go inside the ROS to workspace, SRC, and you are going to find here one configuration file which is named view_odom.rvs. Okay, and then you can open this configuration, this card here, and this one is going to show you already the with all the elements already added. Okay, you have odometry, ground truth, and the filter, which is a third element that we are going to add in a moment. Okay? Yeah? Okay, then with this simple experiment, we have been able to see that our odometry is not reliable, yeah? Because the odometry thought that the robot performed a perfect square, but the square was far from being perfect, right? So how can we then fix this? Okay, so what we are going to do is to use sensor fusion, okay? And for that, we have a package, which is the robot localization package, which implements Kalman filters in order to do this sensor fusion, okay? You have basically two types, which are extended Kalman filter and unscented Kalman filter, okay? But for this kind of setup with mobile robots that move on a 2D plane and EKF, yeah, an extended Kalman filter is preferred, is more than enough, okay? So we are going to use this robot localization package, which is it's already created, so we don't have to reinvent the wheel, and we can use it very easily by just creating a launch file and a configuration file, okay? And configure some parameters for this Kalman filter to work properly, yeah? Then this is what we are going to do now in order to fix, to improve our post data, okay? Why? Because you might say, hey Alberto, but why do I need to do this? Can't I just use the ground truth? Because the ground truth it's telling me exactly where the robot is, right? So why don't you just use the ground truth? Okay. Yes, I mean for the simulation that's fine. Because I can use the ground truth, which is the perfect pose of the robot. But what about the real world? Yeah. When I want to work with the real world, with the real robot outside of the simulation, I'm not going to have access to this ground truth, right? I'm just going to have access to the robot sensors, etc. So I'm not going to be able to rely on this ground truth outside of the simulation, okay? So I need some kind of mechanism to improve my robot's pose estimation, okay? Then this is why I need to use the robot localization package in order to perform sensor fusion, yeah? And what I'm going to do in this example is a very common example, which is that I'm going to fuse the data from my odometry, which comes from the wheels, from wheel encoders, as we were explaining, with an IMU. Okay, and an IMU is another sensor which provides me different information, and it's very common in mobile robots. Okay, IMU gives me information about the accelerations, for example, orientation of the robot, yeah, angular velocities, etc. Yeah, so we are going to fuse the data that I get from the wheel encoders, yeah, from my odometry, with the data that I get from my IMU sensor. Okay. I'm going to combine these two and then try to generate an output which is much more reliable than my current odometry, okay? And this is, we are going to use the robot localization package because it's, basically, it's very easy to set up in this sense, okay? Then, for this, basically, we need just two things. One is to create a launch file that we are going to use to launch the node, and we are also going to generate a configuration file in order to define some specific parameters for our Kalman filter. Okay? All right. So let's go for it then. Let's start by creating our launch file. So let me stop all these. I have many things running here, so let me stop all this real quick. And then let me go to my code editor. And I'm going to go inside the Kalman filters course here. And I'm going to generate 2 new folders, okay? New folder launch, where I'm going to put the launch file, and I'm going to generate a second folder named config, okay, where I'm going to put my configuration file, yeah? So for the launch file, I'm going to name it akf_node.launch.py. You can use the same name that I have here. Launch, new file, paste. Make sure that you don't have any space. There you go. AKF no launch, and then here again you can copy the code directly from the notebook and then paste it here into the code editor, or Control V. There we go. Okay, and say I'm going to do the same with the configuration file. So akf.yaml. I'm going to create this file inside the config folder. Paste. Remove the spaces, akf.yaml, and then inside this one I'm going to copy and paste the contents also directly from the notebook. There we go. Okay. Okay. So I added an explanation here, which here it is. Okay, for some reason this is like gone or hidden. I don't know. Hopefully you have it there correctly. The explanation of the AKF configuration file. Okay. Then yeah. So basically, these 2 things are the things that you need in order to launch a Kalman filter node, in order to fuse data from different sensors, okay? First of all, let's have a very quick look at the launch file. It's very, very simple. All we do is that we are starting an AKF node executable from the robot localization package, okay? And then I am passing to it a configuration file, yes, which I am defining here. My configuration file, it's in the Kalman filters course package, and it's named akf.yaml, yeah? So I launch the AKF node, and I pass it a specific configuration file with my the configuration for my sensors. All right? Yeah. And then in the AKF, you have to specify information for the sensors that you want to fuse. Okay? Let's go over the most important parts here of this configuration file. So essentially here, for example, the world frame, yeah, here we are explaining, we are defining what is the frame that we are going to use for our readings, yeah. In our case, the frame that we are going to use for all our readings is the Odom frame, okay. This is a very typical setup, Odom, yeah. In case that you are using a navigation system, for example, you would use map, okay? In this case, we don't have a navigation system or anything running, so we are going to use as the main reference frame, the Odom frame, okay? Now, this is probably the most important part of this configuration file, okay? Then we are indicating, first of all, one of our input sources, yeah? This is the first sensor that we are going to use for our filter, which is Odom 0, yeah? And then here we indicate the topic where the data comes from, yeah? So our data, our odometry data comes from this topic, ROSBot XL-based controller, Odom, yeah? And here we have the matrix which defines what information we are going to use from this sensor, okay? So this, you can see here this matrix, okay, with 15 values, yeah? And the first 3 stand for X, Y, and Z pose. This is for the orientation, roll, pitch, yaw. This is for the linear, for x, y, and z velocities, yeah, so linear velocities. The 3 next are for the angular velocities, and the 3 last ones are for the accelerations. Okay? Yeah? So x, y, z, roll, pitch, yaw, linear velocities, angular velocities, and accelerations. Okay? Then we have to set to false or true depending on if we want to use that specific information or not from this sensor. Okay? For example, here the first 3 values, we have them to false. This means that we are going to completely ignore the x, y, and z information from my odometry. Why? Well, because it's not reliable. Right? We have seen that the x, y, and z position is not reliable in my odometry data, right? So we cannot really trust them. Same with the orientation, yeah? So what are we actually using? We are going to use the velocities, yeah? Odometry also provides information of the velocities, and these ones we can actually use them because they are much more reliable than the poses, yeah? So we are going to essentially use the linear x and linear y velocities. So we set them to true, and we are also going to use the angular z, the angular yaw, let's say, okay, velocity, yeah, which basically is the rotational velocity of my robot. Okay? So these are the fields that I'm going to be using from my odometry sensor, yeah? The linear velocity is in x and y, and the velocity in the yaw axis, so my rotational velocity. Yeah? And then down here I am defining my second sensor, which is the IMU. Yeah? So where do I get my information from? From this topic, IMU broadcaster / IMU. Okay? So if we come, let me relaunch the simulation. I'm going to run here again the ROS2TopicList command, and then we are going to see right here that we have one of the topics. It's not appearing, just refresh the ROS2Topic list. There you go. And here we have the topic, IMU broadcaster IMU. Yeah? So if we get some extra information about this topic, IMU broadcaster IMU, we are going to see that this topic publishes messages of sensor messages message IMU. Okay? And we can even do an echo to see the messages that are being published into this topic, which are the ones that we are going to be using in our filter. Okay? So here I can see the information published by the IMU sensor, which, for example, we have orientation information, yeah, the orientation covariance. Also, we have angular velocity, linear acceleration. Okay, this is the information that my IMU sensor is providing. Okay, then, yeah, so you have to indicate the topic, of course, and then again you have to decide which information you are going to be using. Okay. Then for the IMU, a very typical configuration is the following. So we are not going to use X, Y, and Z information, basically because the IMU doesn't provide this information. But what we are going to use from the IMU is the orientation information. Yeah. So the yaw, because mobile robots, yeah, just can rotate in the yaw axis. Yeah. So the only information that I am getting here is the yaw. So information about the rotation of my robot, the orientation of my robot. Yeah. Then no linear velocities, but angular velocity. Okay. So if we go again, let me go again here. We can see that we have our IMU provides information about the orientation. Yeah. Angular velocity and linear acceleration, right? So what I am using is the orientation, the angular velocity information, and I am not using, in this case, the linear acceleration. I could, but usually for this kind of setups, it doesn't, it's not very useful to have information about the linear acceleration, okay? So, in summary, I am getting information from the IMU sensor and the odometry, okay? For my odometry, I am using the linear velocities and angular velocity. And for my IMU, I am using information about the orientation and angular velocity, okay? Yeah? There are more parameters here, but essentially this is the most important part of this configuration file, okay? If you want to check in detail all the parameters, you can have a look here at the explanation that I have left, okay? But let me now compile and test this. So let me have a last look here at your comments to see if you have any questions so far. Let's have a look here. Okay. Have we orchestrated the square movement in simulator? I don't understand your question, Dimitris. Sorry. If you can reformulate. If I have two different sources for the same magnitude, let's say x, for instance, which value should I use in covariance matrix? Then the variance of the sensor with higher variance. If I have two different sources for the same magnitude, let's say x, for instance, which value should I use? You should use the one that is more reliable, okay? You should give more weight to the one that is more reliable, okay? So in short, okay, this, well, I am assuming you are talking about these covariance metrics here, right? So essentially this defines how much you should trust the original source versus the filter output, okay? And that basically depends on how reliable are your original sensors, okay? Okay, I understand. Okay, great. All right, so let's, then let's compile this. Colcon build. Well, actually, we need to also update the setup.py, right? Because we have added two new files, and no, we already have it here in the setup.py to install everything inside the config and launch folders, so we can directly come here and compile. Right? There we go, source, and then let's launch our filter, ROS2 launch. It's in the Kalman filters course, and it's named AKF node.launch.py. Okay, there we go. So now we have launched our filter, and this is going to generate a new topic, which is named Odometry Filtered. Here we have it, yeah? Odometry Filtered. ROS2 topic info. Odometry Filtered. Okay? Yeah, this is publishing odometry messages, and we can see that this topic, for example, with the verbose, we can see that this topic is published by the AKF filter node that we have just started, okay? Then, let's start RVs to visualize everything here. And there we go. Here we have RVs. Then let me load the predefined configuration file that I showed earlier, ROS to workspace SRC, view ODOM. Okay. Then here we have in the three different sources now. Okay. We have the original odometry, we have the ground truth in green, and we have also the filter output here in blue. Okay, so I'm going to execute again my node to start moving in a square movement. Let me open another terminal. And let me get a bit closer to the robot here to match. Put this a bit bigger. Okay. Okay, and let me also rotate the view here so that I have them both more or less side by side. Okay, there we go. So yeah, let me start my square movement node, ROS to run Kalman filters course and move in squares. There we go. Okay. So my robot is going to start moving here in a moment. I'm going to be able to evaluate here in RVs what's going on. So you can see that when the robot is moving straight, all the readings more or less are the same. So there are no big errors. Okay. The problems start originating with rotations. Okay. And this is very common also. It's quite common, because of the drifting and etc. So here my robot is rotating, and we should see the red arrows marking a perfect rotation, which is what the robot thinks it's doing. Yeah, there you go. Yeah, so we can see that the red arrows show that the robot thinks that it has done a perfect rotation. But in reality, in the simulator, we can see that it's not. We can also see in the ground truth, which is the green one, that it's not. And also in the filtered one. So the blue arrows are the filtered, the output from our filter. And we can see how the blue arrows are almost the same as the ground truth. Okay? So it looks like our filter is working very well. Yeah? Because actually the blue arrows, which is the output from the filter, indicate more or less the reality of where the robot is. Yeah. So right now the robot is moving in diagonal there, which is what my filter odometry is indicating, and also the ground truth, which is the green one. Yeah. The odometry, which is the red one, is completely off at this point. Yeah. Okay. So here you can see very clearly what's going on. Yeah. And there it goes. There it goes, the perfect square for the odometry, and what's going on in reality, yeah, which is what we can see here from our ground truth and the output of our filter. Okay, so what we can see here very clearly is that our filter, yeah, is doing a great job in actually giving me the real odometry of the robot. Yeah, because we can see it's very close to the ground truth, actually. Okay, so what we can try, for example, now is to change the odometry data for our square movement. Yeah, let's try that, for example. So what I want to try now is to use the output of my filter for my square movement node. Yeah. So let me open again my square movement node, which I have here in the Kalman filters course package, square. And instead of using the original odometry, which is this one, for performing the square movement, I'm going to remove this, and I'm going to use the output from my filter, which is odometry filtered. Okay? So let's see what happens if I do this. Yeah, because it looks like my odometry filtered is much more reliable than the raw odometry, right? So this is the raw odometry from Wheel Encoders. This is the one where I am fusing odometry from wheel encoders with the IMU sensor. Yeah. So let's come here, and I don't really need RVs. So let me just rebuild my package and relaunch it. And let me actually restart the simulation so that we get the robot from the starting point and we can clearly see if the square performed is better or not. There we go. So let's launch our filter here. Again, let me make this bigger. Let's go there. Let's get a better view. Need to get a bit. Okay, there we go. Then source. Let me open RVs just to have also this information. It's always useful. Put this here. I'm going to load my RVs configuration. Open. And let me then rotate here to be side by side. Okay, I'm ready. So let me try again my new version of the square movement node. So ROS to run Kalman filter scores, moving squares. And now, in order to in order to perform the square movement, I'm using the odometry which comes from my Kalman filter, right? So let's see what happens now. Here we go, simulation and RVs here at the site. So far, so good. Let's see when our robot initiates the 90-degree rotation. There it's going. Okay. Okay, so now the rotation is almost perfect. Yeah, you can see that the robot has rotated 90 degrees almost perfectly. You can see that also in RVs with the ground truth in green and the output from the filter in blue, and my raw odometry which thinks that the robot has overturned it, but it has not. Okay. Yeah. Here we go with the second turn, but you can see now that my my square movement node works as it should now, essentially because I am using a proper odometry information, okay? And I have been able to have this much more improved odometry by fusing it with my IMU sensor, okay? This is why sensor fusion is so important in order to produce a reliable post-estimation for your robot, okay? Yeah? Has everyone been able to reproduce this final example? This might be a basic question. How have we programmed the simulator for a square motion? This is this program here, the square.py, that you have here, okay? So you can check it out if you want. This is the source that we are, this is the code that we are executing, okay? I'm not going to go over the code, but essentially what I am doing is to use my odometry data, right? And some basic control equations to get the error, etc., in order to compute how much I am moving forward and how much I am rotating, okay? So for this program to work properly, I need to be able to have a reliable odometry, which initially I didn't have. Now, thanks to sensor fusion and thanks to the robot localization package, I do have a reliable odometry. So I have a reliable pose estimation for my robot. So my program actually works as intended, okay? Yeah? Does all this make sense? Questions, comments? Which dir should I put the AKF node and YAM file? You should put it inside the Kalman filter course package. Okay? This is inside your ROS to workspace. Yeah? And inside the Kalman filters course package is where you should create the launch file and the configuration file. Yeah? Okay, yeah, so don't worry if you weren't able to follow some of the steps. Okay, you are going to be able to rewatch this, pause it, and do things slower. Okay, so don't worry at all. Yeah, and yeah, so for this class, I stopped a bit more than usual. Okay, because I am. Also for future classes, okay, I'm going to try to skip all the most basic stuff, okay, and try to focus on more advanced things, okay. So what I would suggest to all of you, okay, in case that you felt a bit lost during this class, is that you attend to the weekly classes that we are doing, okay. So we are going to be doing weekly classes every Tuesday at the same time, and we are going to be covering many different topics, okay? So in case that you need to practice a little bit more with more basic things like creating packages, compiling, publishers, subscribers, working with topics, all these kind of things, I really recommend you to attend to these weekly classes and even check the past ones if you want. Yeah, you can come here to the past classes, for example, and check what are the last ones that we've been doing, okay? Okay, I cannot get the comments from here, but I can get, I am able to get them here in my second computer, so let me let me go over them here. Which dir, okay. Does the Kalman filter node work as a publisher? Kind of, yes. So the Kalman filter node, in the end, my Kalman filter node is generating let me stop this, is generating the odometry filtered topic, right? This is generating this topic here, odometry filtered, yeah, and it's publishing the pose estimate of the robot in this topic. So yes, the Kalman filter node is publishing this odometry filtered topic. So in that sense, it is acting as a publisher, yeah. Where can I find the square.py? The square.py, you have it here in the Kalman filters course, okay? Square.py. Okay? Yeah? Is the AKF node agnostic of the motion model? No, it is not agnostic of the motion model, okay? It's not agnostic, so it matters, the model, because it uses the motion model in order to predict the next step, okay? So no, it is not agnostic, and you can change it in the configuration, the motion model, okay? Thank you, Alejandro, for your nice words. My pleasure, my pleasure. Okay, yeah. So, at the beginning of the class, I went a little bit over this. Yeah, but basically how the filter works is through two main steps: prediction and correction, okay? In the prediction step, the filter uses the motion model to estimate the next state, yeah? And then in the correction or update, it compares this prediction that comes from the motion model. It compares the prediction that comes from the motion model with the data that comes from the sensors, okay? Yeah? All right, so yeah, thanks everyone for attending. Let me remind you that we are going to be having these classes on different robotics concepts. In my case, I'm going to be here monthly, okay, talking about different topics, but we are going to be having different classes weekly, so stay tuned, okay, for much more practical classes like this one, where you are going to be able to learn while doing, which is the best way of learning, in my opinion. And yeah, thanks again for all of you for attending, and I hope to see you all in the next one. And as always, until then, keep pushing your robotics learning. Bye-bye.